Okay, so welcome everyone. It's a pleasure to introduce Leo Radzihovsky, who's going to kick off this year's colloquium series. Leo got his PhD from Harvard, then he did a postdoc at University of Chicago, and after that moved on to faculty position at UC Boulder, where he's been ever since. I view Leo as very much a role model for condensed matter theorists. For one, he has extremely broad interests, which on one end include topics in soft condensed matter, and on the other side, various problems in hard quantum condensed matter. And despite having such broad interests, he managed to think very deeply and has made a lot of lasting contributions throughout his career across that spectrum. Apart from research, he's also had a major impact on our community as a co-founder and the director of the famous Boulder Summer School. I think many people here are alumni of that school, and it's been around, I believe, now for 20 years. Is that right? Yeah. 20 years, and has helped train generations of new condensed matter physicists, many of whom go on to become leaders in their field. So today, Leo is going to tell us about a fascinating problem that bridges some of those broad interests that I mentioned, in particular, relation between so-called Fracton states and elasticity theory. So please join me in warmly welcoming Leo for today's talk.
All right. Well, thank you for coming, and it's a real pleasure to be back at Caltech. I've been learning a lot of interesting things that are going on here, but also it's always great to see old friends and catch up on what they're doing. So today I want to tell you about a quantum state of matter that exhibits so-called Fracton order, and the subject of the talk is to explain what that is, but in particular to give you a perspective to that quite exotic order of this quantum matter or quantum models that comes from in some sense, from soft condensed matter physics, and namely its relation to a very ancient and well-understood subject of elasticity and crystals. Okay. Well, so this is a colloquium, so I would like to, before delving into details, I want to kind of give you a perspective from a broader condensed matter perspective at the risk of maybe boring my condensed matter colleagues. So the subject of condensed matter occupies itself with thinking about phases of matter and characterizing them, classifying them, distinguishing them. And so, if you think about a crystal versus a liquid, there's something different between them, and in fact, the difference is the sort of a symmetry, breaking of symmetry, translational symmetry, rotational symmetry. A liquid is homogeneous isotropic typically, unless you're dealing with, let's say, a liquid crystal. A crystal breaks those symmetries down to discrete symmetries. And so that's why, for example, a phase boundary line between a crystal and a liquid must rigorously continue forever. It cannot have an endpoint. On the other hand, if you think about a liquid and a gas, although we learn in elementary school about these being the two of the 3 or 4 phases of matter we learn about, but actually they're only quantitatively distinguished by their density and not really any qualitative property. And as a result, this phase boundary between a liquid and a gas can actually end at a critical point, and if you crank up temperature and then change the pressure, you can actually go around that critical point and continuously transform one to the other. On the other hand, one can ask a more broader question. Imagine you have 2 disordered phases of matter, so to an eye they look disordered and similar, much like a liquid and a gas. You can still ask, is there some property that you're not sensitive to, or your conventional experiments are not sensitive to, that nevertheless creates some kind of a qualitative distinction between 2 disordered phases of matter? And if that was the case, then there wouldn't be a possibility of ending that phase boundary, because there would really be a qualitative difference. So while sort of in early schooling, this is the kind of picture that we get treated to of condensed matter, in reality, the world and nature, thankfully, is much more interesting, and so it gives us a lot to work on as condensed matter physicists. And so to my eye, this is really, this is just a small cross-section of the kind of hundreds of, maybe thousands of condensed matter phases that we study. And it's kind of amazing how diverse and broad range of phenomena you're looking at, even in this small cross-section. But one can ask, what is the unifying principle? What makes all these things this kind of the same fall under the same umbrella of study, namely condensed matter physics. And it's really only two ingredients sufficient. That's one is strong interactions, and two, some kind of a macroscopic number of degrees of freedom. If you have those two ingredients, you have condensed matter system. It doesn't matter what the constituents are. Those constituents could be polymer in this piece of rubber, liquid crystal molecules, vortices, grains of sand, or electrons and spins. They all form condensed matter physics because there's macroscopic number of them and they strongly interact. And that is really at the heart of the richness of the subject, and it was beautifully summarized by a famous quote from Phil Anderson. And in fact, although this is somewhat poetic, we have a very, much more quantitative and rigorous way of thinking about this, going back to Noether and Landau and culminating in renormalization group and effective field theory formulation of condensed matter physics by K.G. Wilson. And in fact, we think of states of matter and the description of states of matter in terms of these effective field theories. And here I have a laundry list of some of the things I could think about from the top of my head, where there's new emergent laws of nature emerge out of microscopic degrees of freedom once you start looking at a macroscopic matter at long scales, low energies, low frequencies. For example, Navier-Stokes equation. Fundamentally, you have some particles, but at long scales, at low energies, you have Navier-Stokes equation, which encodes particle number conservation and momentum conservation. What emerges is the new laws of nature, new phenomena like waves and shear flow and viscosity. And you can go down this laundry list, ending with even, maybe classical gravity. You can think of as an effective field theory of long wavelength field theory of some maybe microscopic theory. Okay, so that's sort of a general remarks about states of matter, states of condensed matter physics. But now let me get a little bit more into it in a little bit more detail. Most phases of matter that we're familiar with are sort of follow what we call Landau paradigm. So Landau taught us how to think about phases of matter, how to organize this soup of variety of phases that we see here and many more. And what we learned is that phases of matter are characterized by different patterns of symmetry breaking. So a crystal, a liquid crystal, a magnet, a superconductor, there's various, maybe superconductor is actually not a good example, maybe a superfluid, are different patterns of breaking symmetry. And, that symmetry is characterized, that broken symmetry is characterized, as Landau taught us, by a local order parameter. Think about it as a magnetization or optical anisotropy tensor, let's say in a liquid crystal transition. And its role of this order parameter is to distinguish the two phases. And here I indicated just schematically an isotropic liquid phase, which is what you would get if you took your laptop and warmed it up to sufficiently high temperatures, and the liquid crystal between the two glass plates actually left the pneumatic phase. And then if you lower the temperature, and hopefully, most of the time you're operating, whether you're going skiing or on the beach, you're robustly in this regime. You're inside a pneumatic phase where you break rotational symmetry of the isotropic liquid phase. It's still a liquid in the sense of it's translation invariant, but it's no longer isotropic liquid. It's an anisotropic liquid, so we call that a pneumatic. And you can see here, if you look between cross polarizers, this guy looks black between cross polarizers because it extinguishes polarized light, while this guy exhibits this beautiful Schlieren texture, which has vortices, and that's just a consequence of this optically anisotropic medium that you get when the molecules order inside a liquid phase. But, I can repeat these words for any of the, familiar phases of matter. The point is there's an order parameter that distinguishes the two, and it's a local order parameter that you can touch and feel, and there's a local response to it. And what we're heading towards with this as a background is towards thinking about phases of matter and transitions where this is no longer going to be true. Okay? And one observation also is that goes along with this is basically if you think of a many-body wave function that describes these states, if you think about quantum state, it's basically a product state. It's short-range correlated, so you can think of it as it's very closely related or continuously connected to a product state. a non-interacting state. But in the last couple of decades, it's become clear that there are phases of matter that go beyond this Landau paradigm of local order parameter symmetry breaking. And by now, this is a well-known story. Experimentally, probably the best example is the fractional quantum Hall effect. But much of this activity was actually stimulated by discovery of high-temperature superconductors, where there was a lot of observation of anomalous behavior which didn't neatly package into the Landau's paradigm. And so this is what I will call, for the purpose of this talk, I'll call conventional quantum liquids, by which I mean states of matter, quantum states of matter, so zero-temperature states of matter, that are quantum mechanical. Liquid is in quotes. It means it's a disordered state of matter. So there's nothing, locally you look, there's nothing distinguishing about it, but nevertheless there's something underlying that distinguishes one type of a quantum liquid, disordered quantum liquid, from another disordered quantum liquid, as happens in the fractional quantum Hall effect, for example. And although experimental realizations, smoking gun realizations of this are really missing with only a couple examples, the fractional quantum Hall effect, and that's basically it, but my colleagues mathematic colleagues who are more into the subject can correct me. As far as I know, this is kind of the only example I know of outside of one dimension. Theoretically, there are many models now, ever-growing class of models that exhibit this phenomenon. So there's absolutely no doubt that there's a possibility of, theoretically, it's in principle possible to have phases of matter which fall outside of this symmetry-breaking Landau paradigm. And all these models, exhibit very common features that we, learn to appreciate and love. So they don't have an order parameter to characterize the phase. They have quasi-particles that are non-local, meaning they're non-local in the sense of it takes infinite number of microscopic degrees of freedom to create actual, effective degree of freedom in terms of which the theory looks weakly coupled. And those effective degrees of freedom, the quasi-particles, are a fraction of the microscopic degrees of freedom. So we call them anyons, and they usually have non-trivial statistics and non-trivial charge, fraction of an elementary degree of freedom. And they usually appear, as indicated in this image that I took from Liam Belenz's review on spin liquids. These particles appear at the ends of strings. So, for example, you have a string of, we could call electric field line, and there's some excitations that appear at the ends of it. You could call this electric charges appearing at the end of an electric string field line. And equally, in this model, which is actually, this is an illustration for this very famous model due to Kitaev, the toric code model, very beautiful and simple and exactly solvable model where you can really work everything out. There's also excitations that are magnetic excitations that appear at the end of the magnetic field line. And so because of that, these particles, while non-trivial, they can move freely. They have statistical interactions, but nevertheless, they can move freely. You simply if this guy wants to hop over one side, you simply grow the string by one lattice. And that's a local move that you're able to do. And so the particles are actually quite mobile, but they're even in the absence of Coulomb interaction or any kind of a on-site interaction, they have statistical interaction, non-trivial statistical interaction. So these states exhibit what we call topological order, which is these fractionalized excitations as part of it. But they also, if you study the system on the non-trivial manifold like a torus, you'll discover that it has a ground state degeneracy, which is robust to any local perturbation. And also we say, unlike these Landau-like states, familiar states, we say that these states exhibit long-range entangled order. And that's kind of a summary of their topological, what we say these phases are topological. And so all of this is very beautifully and simply packaged in so-called gauge theories, and there are different types of gauge theories. And so gauge theories are enough to, as far as we knew up until quite recently, are enough to capture these kind of quantum topological states of matter beyond Landau paradigm. And so just to give you just a brief idea, you can start out with a simple, some kind of a model, lattice model of actual microscopic degrees of freedom. For example, here there are spins living on parallel core lattice. And there's some, there's usually, in order for this to emerge, there's usually some kind of a local constraint, energetic constraint on your degrees of freedom, that if you confine yourself to the low energy sector of your theory, that looks like a constraint. And when you satisfy that constraint, then these microscopic spin models begin to look like, you can drive them, or you can find them to be in a phase where the phase is more appropriately described by a bunch of strings that have Bose condensed. And by Bose condensed, I just mean you have just like you have a condensate of particles in a bosonic model, here you have a condensate of strings, which means the many-body wave function is a superposition of all different string configurations, let's say, of electric field lines. So if now you want to produce a particle, the particles appear just like broken strings. There are two ends of the string. Those are the electric, the charged excitations. You can call them electric charge excitations or magnetic charge excitations, depending on, what these lines are. And those particles are deconfined because once you have a condensate, if you move the string, the ground state has infinite superposition of all possible string configurations. So there's not really in those kind of condensate of strings, you have no line tension connecting those particles. So there's no energy per unit length. And so then you can separate these particles. They move freely with just some statistical interaction. And so what emerges, very much in the theme of my comment about emergence, is some kind of an effective electromagnetism, that describes these microscopic degrees of freedom. But this happens at low energies when the constraints are satisfied, at energies below the constrained energy. Okay, so that's emergence in these topological states of matter. So what I want to tell you about is, now shifting really to the subject of the talk, is another class of topological states of matter, which somehow, as far as we understand, and this is now vigorously studied, doesn't fall into either of these paradigms. It's not, it's clearly not Landau paradigm of symmetry breaking, but it's also not even, it's even much more exotic than these topological states of matter of spin liquids that I just described. And so we call them fractons. Well, they exhibit excitations that are called fractons. Those fractons, their claim to fame is they cannot move. You can create an excitation, but that excitation cannot move. So that's kind of interesting, and there's lots of interest in it from the point of view of quantum information, robust quantum memory, but I'm more interested in it as a state of matter. So that's what I want to tell you about. And just in a formal outline, there are many sort of complementary descriptions of these models, but I'm going to focus on one type of a description and going to gloss over all the others just in the interest of time. And the description will be in terms of a gauge theory, but a tensor gauge theory where instead of having vector potential and electric fields that are vectors, you'll have tensors. And that theory will encode Fracton behavior. Then I'm going to remind you about standard things about elasticity. It should be very simple. And then I'm going to connect these two by a so-called duality transformation and show you that, in fact, in disguise, this theory of elasticity of a quantum crystal is actually in disguise or dual to a Fracton theory of these tensor gauge theories. And then I'll give you some more, elaborations on this if I have time. Okay? But really the goal is to get to this duality. Okay, so what I want to tell you about is this Fracton quantum matter. I called it Fractonicity in my title slide because Fractonicity nicely rhymes with elasticity. So the original set of models, and in fact the renaissance in this field comes back to Caltech. There was a student of John Preskill, Ha, who was a quantum information theorist and invented this so-called Ha code, and since then proposed many other models, but actually the subject goes back, as you can see here in the list. In retrospect, while Ha's paper goes back to 2011, in retrospect, actually there's a paper by Claudio Cimone that was with a different goal, but in fact Claudio Cimone in 2005, the model that he proposed actually has this fractonic order model, fractonic order. Anyway, so what are these models? These are just some lattice models with quantum spins sitting on the lattice sites on the bonds or links of the lattice. For example, the simplest one, you have a hypercube well, let's say in 3 dimensions you have a cubic lattice, and you have spins living on the bonds of that lattice, and the Hamiltonian consists of terms which are just basically interaction of those spins. And I don't want to get into details. I've written them out here, but it's not really important for what I'm going to say. You just want to understand general picture. One observation is that there's a limit of these models where these operators that the Hamiltonian is composed of are commuting projectors, meaning you can diagonalize each term independently, and that's what allows you to solve the model exactly. And this one is the so-called X-cube model, which is very beautiful. You can, again, it's very much like Kitaev's toric code. You can work out everything you want about this X-cube model, and so it's very illuminating to think about this model. But the thing that was of interest to this talk, and it was interest to me, is really the properties of these systems without looking at the details. So first, they also have non-local excitations, meaning these are spins, but the actual excitations are these little blue cubes, which are the Fracton excitations. So if I flip one of these spins, and here I flipped all the red bonds here, flip the spins on all these red bonds, it's the membrane operator. What I create is not 2 excitations like I did in the gauge theory, positive, negative charge of an electric field line at the ends of the electric field line. What I do is I create 4 excitations, or some cluster of excitations. As a result of that, these particles cannot be moved individually. Like if I have one of these corners, blue corners, I cannot move it. I can move them together in some way by growing the membrane, by flipping more spins, but I cannot move one particle. If I attempt to move one particle, I have to add energy because I'll end up inadvertently creating 3 more particles if I want to move any one particle. So it's just not possible. And that's just the rule of the game of these Hamiltonians. They have that property. So again, these models, they have Fracton order because particles appear not at the end of a string, but at the end of some extended object like a membrane or a fractal in the Haas code. And so they're immobile, so we call those fractons. There's also other particles which are maybe dipoles of these charges, fractonic charges. Those guys can move, but often they move in some subdimension of space. For example, dipoles can either move along the dipole in some models, or they move in the plane perpendicular to the dipole. They're not able to move and explore full 3-dimensional space in which they live. Okay, so those are the kind of the properties that are some of the features of these systems. And since original papers, there's been barrage of work, and this is just a tiny little tip of the iceberg of different ways of creating these models, from lower order models. For example, you can take the X-cube model due to Vijay, Hai, and Fu. You can think of it as gauging, as subsystem symmetry, whatever those words mean. Maybe this is a little bit more meaningful. You take lower order models like the toric code models of Kitaev and make a stack of them in all 3 directions, and you can build Fracton models out of the lower dimensional objects by coupling them together in a certain way. You can take chains of one-dimensional systems and couple them together and build fractonic models. There are part-time constructions. There are many types of constructions. Some of this work is going on actually here in Xie Chen's group, and that's represented by this paper, but there are many others, some going on here. But the one that I want to focus on is what I mentioned as the higher rank tensor gauge theory formulation of fractons. Okay, so it's kind of orthogonal to all of these, but it's very beautiful, and I can say that because it's not due to me. It's actually the observation that the higher tensor gauge theories, which have been studied in the literature for a long time, but it was not appreciated until Michael Pretko in 2016 pointed out that these theories actually have Fracton order in them, or Fracton property in them. And so what I mean by tensor gauge theory is that your gauge fields and your electric field and the gauge field are no longer vectors, they're actually symmetric tensors. So you can see here, this is the electric field, and it has 2 indices, and so it's a symmetric tensor. And not surprisingly, if it's a symmetric tensor, if I want to write down a generalization of a Gauss's law, generalization of the Gauss's law is a double divergence on both indices of that electric field tensor. Okay, complete analogy with a single divergence in the ordinary Gauss's law. Okay, so let's see where that takes us. So this is the main player, and I haven't defined what tensor gauge theory is except to tell you what the variables are. But so first I want to tell you how incredibly compact and powerful this observation is, that there's this double divergence. So these are the charges. These rows are going to be the fractons, and EIJ is the tensor gauge field, and the Gauss's law has this double divergence. So as in usual gauge theory, of electromagnetism, where you have a single divergence, if you have that single divergence and you ask what is the total charge in some volume, then that total charge is conserved. It can only be changed it cannot be changed locally. It can only change by having things enter the boundaries, and that's because rho, charge density that you integrated, can be replaced by a divergence of electric field, and then you integrate, that's a total derivative, integrates to the boundary, so you cannot change it locally. So that just tells you there's a charge conservation in the ordinary gauge theory as well as here. But in addition to that, because there's a double divergence, there's also something else that's conserved, and that's the dipole. If instead of looking just the integral of rho, I look at the integral of rho times the vector r or vector x, meaning the position of where that charge is sitting, and do that integral, that's the total dipole pi. Because there's a double divergence, without doing any math, you can appreciate that you can integrate by parts twice now, and again, reduce the integral to a surface integral as indicated there, and so dipoles are conserved. Okay, so you might say, okay, so what? Well, that immediately very compactly encodes Fracton behavior in the way I want to show you now. But before I do that, let me just tell you once and for all what is a tensor gauge theory. So U1 symmetric tensor gauge theory has two fields. They're canonically conjugate, electric field. And so I'm going to focus in 2 + 1 dimensions, or 2 spatial dimensions, 1 time dimension. So there's an electric field, EIJ, and there's a vector potential, AIJ. These are two symmetric tensors, and they're canonically conjugate, like P and Q in the harmonic oscillator. And then, just like in ordinary gauge theory, ordinary electromagnets, there's an E squared term plus a B squared term, where B is just a curl of A, a funny curl of A. Okay? You can also think of it as just harmonic oscillators in a sense. There's a P squared and a Q squared and P squared, or E squared plus B squared. They're canonically conjugate. Okay, so that's the theory. And now you have this Gauss's law, that double divergence Gauss's law that's imposed. And what's amazing is, in addition, so I already mentioned there's a conservation of charge, but there's a conservation of dipoles, and that immediately gives you Fracton phenomenology in the way I'm going to show now. And so suppose I want to move a charge. When I move a charge, a process of moving a charge is actually a process of creating a dipole, if you think about it. Because if I have a charge here, to move it here, I have to destroy it here, create it here. What does that mean? I've added a dipole. But I'm not allowed to add dipoles locally. The total dipole number is conserved. And so I'm not able to move a charge. And so let's suppose I have this charge and I want to move it. If I want to move it from here to conserve dipole, I have to add an opposite dipole to cancel that dipole. So overall, I'm adding a quadrupole and not adding a dipole. But now this guy is gapped. There's some energy cost, and so I can't create that object unless I add some energy. On unshell, that's not a process. So it's kind of an incredible thing. These models are such, and this gauge theory encodes that so compactly. You have a translation invariant system. So you can put this guy anywhere, but once you put it there, you can't move it. It's kind of an amazing thing. We're used to, in condensed matter systems, where you have disorder, random potential, that things are localized as a single particle, in a single particle well. And then you can't move it because it takes energy to get it out of there. But here, it's completely translation invariant. Every side is identical, but once you put it there, that's it. You're stuck with it. Okay? But of course, the way you do it, you create some group of particles, and now you can move them in some coordinated way. Yeah, so this is not allowed. But a dipole can move, because the motion of a dipole is an addition of a quadrupole, and that's not conserved. Although it could be conserved, and I will talk about theory where it is conserved. Okay, so that's the background, if you wish, and that's the introduction to the second part, what does Fracton matter, and the tensor gauge theory. And so, very naturally, in fact, when I first heard about this was a little bit beyond my, I thought these are too sophisticated of models, because I first learned them, thinking about, I first heard it in the context of Haas code, and I thought this is just beyond my imagination. And also, it doesn't seem like something that's ever going to be connected to any physical realization, because the spin interactions is extremely, involves many spins, So then, but so naturally a question arises, is there a physical realization? And in fact, my answer to you, and then that's what I'm going to demonstrate next, is that indeed, and it's just something very, very simple, in some sense mundane, just a two-dimensional, at least I can demonstrate it for a two-dimensional quantum crystal. Okay? And I'll define what those terms mean. And so when I first heard about fractons, not understanding what the models are, but understanding these properties, immediately kind of a light bulb went off in that I realized that I've heard about this subdimensional behavior of subdimensional mobility of particles. Namely, I've heard about it in studying motion of topological defects, namely dislocations in the crystal. And that's a well-known phenomena, and so that I want to tell you about it. So if I think about a crystal, and let's focus on 2 dimensions for the rest of the talk, in addition to phonon degrees of freedom that you think about, there's also topological defects. So one type of topological defect is a disclination, where you add, let's say on this hexagonal lattice, you added 2 pi over 6 wedge of matter, or you subtracted 2 pi over 6 wedge of matter. So that's a disclination. So this is like, think of this as +1 charge, this is -1 charge. This is 7-fold coordinated point. This is 5-fold coordinated point. You can think of it as a vortex in the crystal structure. In addition, you also have dislocations. And dislocations actually turns out to be a dipoles of a plus and minus. So that's already something that reminded me of it. This is a dipole very much like dipoles in the fracton theories. In fact, I'm going to claim that these are fractons, and these are dipoles of those fractons. And it's well known that dislocations actually have a very difficult time climbing, meaning if this is a dislocation, as you see, I've inserted an array of atoms that ends here, and if the dislocation is defined by this Burgers vector, which is illustrated here. So dislocation climbing means motion of this point, imaginary point, up, perpendicular to the Burgers vector. And actually, the dipole is perpendicular to the Burgers vector. So it's a motion of a dislocation along the dipole moment, or perpendicular to the Burgers vector. So it cannot do that, because if it did that, it generically cannot do that, because if it did that, you lost an atom. If atoms are conserved, you're not allowed to. Conservation of atoms forbids that motion. You need a vacancy interstitial to eat up that atom in order to move up. On the other hand, it could glide no problem. So this is an example that kind of was immediately, rang a bell in my head when I heard about fractons, where, this is an example of excitation which is subdimensional. It lives in 2-dimensional space in this case, but it's quantum, but under ordinary dynamics, it cannot move, can only move in 1 dimension and not in 2 dimensions. Okay, in the absence of vacancy interstitials. So if that's the case, and I kind of start thinking about this more and formulate this conjecture that indeed topological defects have some relation to fracton matter, but if that's the case, that means the disclinations are actually also immobile. And I've never heard of discussion of immobility of disclinations. So suppose I create a disclination. How do I understand in elementary terms, without appealing to any gauge theories or anything like that, that disclination, I cannot move it? I create it, but I can't move it. And there's actually a very simple way to understand it. So let me explain one way. So if you think of a disclination, it's actually, one way to think of it is a array of dislocations. Very much like you can think of if you have an array of dipoles, electrical charged dipoles, the end of those dipoles is really like where the charge is. So if you think of it that way, then suppose I wanted to move, so these are dipoles, these are the dislocations, an infinite array of dislocation that ends. So this has non-trivial disclination charge. So suppose I wanted to move this point, let's say down. Well, how do I do it? I need to create a dislocation. Very much like I discussed, motion of a particle is addition of a dipole. But what does it mean to add a dislocation? It means I'm adding an infinite array of atoms. So in terms of microscopic degrees of freedom, it's an extremely non-local process. You don't have at your disposal in your Hamiltonian. So if your Hamiltonian is written in terms of microscopic atom degrees of freedom hopping around, no matter how quantum they are, no matter how mobile they are, as long as crystal order remains, this disclination cannot hop because you cannot add a dislocation. Okay, so now, so that's the story. Yeah.
Sorry, but then if your dislocations can glide still,
How what?
So you're arguing that the same way a dislocation can't climb, the disclination can't move downward?
Right.
Can it still fly?
The dislocation? Or disclination? No, it's completely immobile. It's just, this is the simplest picture where I can illustrate this. I can make more elaborate argument why it can't move in any direction. Okay. So with that background, that's basically the message. And so the rest of it is, so that's the conjecture that I put forward, that quantum crystal, topological quantum crystal, exhibit this Fracton order of tensor gauge theory. So now so what one wants to do now, to go beyond that conjecture, actually demonstrate it mathematically. And that's what we did next. So to do that, let me give you some crash course on elasticity, just define some variables. So, how do I describe a crystal and elasticity? Well, there's some deformation. That deformation is described by a phonon variable, u. Then you can define a strain tensor, which is basically a metric of the space. It's in the harmonic approximation, there's just a symmetrized derivative or gradient of the phonon field u. And now you just construct a Hamiltonian. The Hamiltonian is just a bunch of coupled harmonic oscillators. There's a p squared plus coupled harmonic oscillators, and Cij is the elastic constants that characterize which crystal you're talking about, what the symmetry of the crystal is. Okay, that's kind of the most general way to write a harmonic theory of elasticity. And the topological defects, in a little bit more detail, are singular deformations of this phonon field. So, for example, a disclination is actually a vortex in the bond angle theta, which itself is a curl of derivative of u. But, this is just mathematical expression. Pictorially, it's the same thing as I already showed. And dislocation is the curl of a gradient of displacement field. That's what a dislocation is. And in addition, of course, you also have vacancy interstitials that I already mentioned. So now what I want to do is I want to show you how you can actually demonstrate that there is a duality between the two theories, that the two theories are actually mathematically connected. But before I do that, let me remind you about duality, the simplest duality we know of that's very much related to this, and that's boson-vortex duality. So imagine I have a bunch of bosons. They, at low temperature, at zero temperature, they'll form a superfluid. So I describe that fluid in terms of gradients of the phase field, that's the currents. And those currents can have smooth deformations or smooth configurations, but they also can have vortices. And the vortex is defined by a non-zero curl of J, so as indicated in the picture. So wherever you have non-zero curl of J, that's where you have a vortex density at that point. Now, and the Hamiltonian is very simple. It's just a gradient of phi squared. Since grad phi is current, that's just the kinetic energy. That's J squared. And n squared is just the atom-atom interaction, short-range interaction. And then these guys are canonically conjugate. That's what makes it quantum mechanical. But now, imagine in your mind rotating these J's by 90 degrees. So now, rather than circulating, they're going to point like a hedgehog out in 2 dimensions. And so you're going to get this. And so if you call 90-degree rotated J, call that E, then what this law means, this vortex configuration, just corresponds to a Coulomb configuration in electromagnetism. And so meaning E is just rotated J. So then if I rewrite this Hamiltonian in terms of these new variables, it's very simple. This is J, but rotated J is still E squared. That becomes E squared. So kinetic energy becomes just E squared. And N squared turns into grad A squared. Okay? So this is the electromagnetism. So this is the dual. What we say is a bunch of bosons are dual to electromagnetism, where E and B are related to, B is related, flux density is related to density of bosons, and electric field is related to the current. And topological defects are related to the charges, electrical charges. Okay? So now what we want to do is we want to repeat this, but just for the tensor gauge theory. So if you squint your eyes, it's basically the same. I mean, there's some underlying new things, because this is not a Fracton theory, but the one I'll get is a Fracton theory. But, in terms of manipulations, it's very similar. There's just an additional index, because rather than having just grad phi, I have a grad u. And u is a vector rather than scalar. Okay? There are two Goldstone modes, the ux and uy phonons, rather than just a single phase field phi. But the idea is the same. So here's the duality. I'll just fly through this because the details are not important. I'll just put it up there for completeness. So here's a Lagrangian velocity squared, kinetic energy squared plus harmonic spring squared. The disclination density that I disclination structure is encoded by double derivative, rotated double derivative on uij. That's the disclination charge, and this is the curl of B that I argued for when I think about it, a row of dislocations. So this is the analog of this condition. This condition locates where the vortices are in terms of current circulation, and it's a single curl. This guy locates, it's a double curl if you wish, which locates where the disclinations are, and curls of dislocation. And now, this equation of motion, you won't be surprised, but you can derive it explicitly, is actually contains in it conservation of momentum, which is nothing more than Newton's law. It just says time derivative of momentum equals to the gradient of the stress. And stress is like a conjugate variable to the strain. So that's a law, conservation law of momentum. But now, if I look at this conservation law of momentum, I can just turn my head sideways and think and make an identification. Think of momentum rotated by 90 degrees by this epsilon symbol as the magnetic field, and think of the sigma ij rotated on both indices by 90 degrees is the electric field. So stress is the electric field. Momentum is like the magnetic field up to some rotation, just like I rotated the currents into electric fields. But now, what does this law become? Just becomes Faraday's law. dP/dt becomes dB/dt. And the divergence of stress becomes curl of E. It's just Faraday's law. We know how to solve Faraday's law. You just introduce gauge potentials. B is curl of A, and E is a time derivative of the vector usually it's a time derivative of vector potential. Now it's a time derivative of tensor potential. And then plus double derivative, double gradient of the scalar potential, A0. There's a gauge transformation, and you can derive Lorentz force and equivalent. And so the bottom, so all of what I've told you about can be summarized in this dictionary. Here's the theory of defects in crystal. Disclinations is encoded in this double curl. Dislocations are dipoles of and so these are going to be the fractons, and this law of topological density is encoded, translates into double divergence of the Gauss's law. The disclinations are fractons. Dislocations are dipoles of disclination, so they become dipoles of fractons. Gauge modes are like phonons. Electric field is like strain or stress. Magnetic field is like momentum. And Faraday law maps onto Newton's law. Okay, so that's really all, for the most part, that's all I wanted to tell you. Like, if you have followed that, that's really the message. Okay, the rest is just I want to give you some elaborations on a few other cool things that we've been doing and thinking about. So one thing, and this is a little bit for the experts, but I'll mention it. So there's something unsatisfying about tensor gauge theory because it's so unfamiliar and kind of doesn't connect to anything. It doesn't connect to even these exotic spin liquid states of matter. So it'd be nice to have some description, maybe equivalent to this tensor gauge theory, which is closer and easily goes over in some limit to the familiar non-fracton gauge theories. Okay? And so there's a formulation or reformulation of what I've just done in terms of vector gauge theories. But what it requires is not one vector gauge theory, because one would not be fractonic. It requires a coupled vector gauge theories. So if you're in 2 + 1 dimension, it requires 3 vector gauge theories. So there's a little e and little a. That's one vector gauge theory. Notice these are vectors. And then there's 2 additional vector gauge theories, a and e, and they're labeled by k. By k. That's their flavor. Or here are the 2 Gauss's law. And there's a strange thing that the components of this electric field appear as charges in the Gauss's law of this electric field. So like EX component is a charge for the, or EA component is a charge for this Gauss's law for the capital EA theory. And, you can put these in a lattice, so there's an underlying lattice where the little E's and A's live on bonds of the black lattice. And then there's 2 more lattices. One shifted up, that's the blue lattice, and one shifted to the right. On the blue lattice, you have the B, E sub B's, capital E sub B's, and on the red lattice, you have capital E sub A's. And then what you get is, as indicated here, and then what you get is a fairly conventional three vector gauge theories. Here's the E squared plus curl of A squared. That's the usual one. There's two of them, K being A and B. So there's two copies of this. And then there's a little E and A. That's the E squared plus curl A squared. But then there's a non-trivial coupling where the curl of A couples to an antisymmetric combination of A and IJ. That's kind of interesting because this actually has some, so I derived this in a specific example, thinking about a duality of a crystal. But actually, exploring with Mike Hermele and now and Marvin Chi, a really talented student in Boulder, this structure is actually, this has some structure and maybe general implications of constructing this kind of a coupled vector gauge theories coupled in this way. So, normally when you have matter, it's a scalar, like a phase of a matter field. So a gradient of that couples to a vector potential. So you get grad phi minus A. That's the minimal coupling. Here, the matter is the gauge field little a. That looks like matter. So you take a curl of it, and that couples to what looks like a two-form, which is the antisymmetric part of the capital A field. So the coupling is very non-trivial. It's a spin orbit-like coupling, but nevertheless, so it looks like one-form matter minimally coupled to two-form gauge field, rank 2 gauge field. Okay, so that's one embellishment. The other thing I wanted to mention is this. So far I've talked about this tensor gauge theory. Here it is. Actually, before I get to that. So far I talked about a lattice. A lattice has these elastic degrees of freedom and topological defects. But what I've forgotten about is vacancies and interstitials. So I have to, if I'm describing a quantum state of matter, I have to mention what are the atoms doing. So imagine, just for simplicity, and this is the case we worked out, you consider bosonic crystal, meaning a crystal of bosonic atoms. Well, I need to say what those bosons are doing, the atoms themselves are doing. I can't just throw them out. Okay? If they're gapped, then there's nothing else. I can integrate them out at low energies below that gap, and then I have what I've described for you, a tensor gauge theory. But if those bosonic atoms are not gapped, and we know that they may not be gapped because they can both condense and you can get a supersolid, then I need to include them. Here they are. There's some description of the atoms of vacancy interstitials themselves. Those guys themselves can become superfluid, and the resulting, and then there's some coupling between them. The resulting state of matter is well known, at least theoretically. One is a monoinsulator, I call it commensurate crystal, where these guys are gapped, vacancy interstitials are not there. And the other one is the incommensurate crystal, where there are some vacancy interstitials in your ground state. That's what we call supersolid. It's a crystal, but it has superfluid properties in the sense of vacancy interstitials have both condensed, while still have crystalline order. And so this is, so that's the lattice side. So imagine now I repeat all the steps I went through by dualizing these theory. Well, you wouldn't be surprised. I already try to convince you in my process of discussing duality. This guy becomes an ordinary gauge theory, vector gauge theory. This guy becomes tensor gauge theory. So together, they're just going to be a sum of those plus some coupling. Okay? And look, I have two types of crystals. Commensurate crystal and incommensurate crystal, supersolid. That means I can immediately predict there are two types of Fracton phases. One corresponding to this one, which is the one I described, and one that corresponding to this one, which I have not described. And so, yeah, so indeed you get a vector gauge theory plus a tensor gauge theory plus a coupling between them. And so supersolid corresponds to a Fracton state of matter where dipoles are mobile. Why? Because vacancy interstitials have both condensed. So now from the point of view of crystal, those dislocations can move all around. They can climb and glide because they're condensated vacancies that they can eat up. I broke the U1 symmetry of charge conservation or atom conservation by both condensing vacancy interstitials. On the other hand, the original one I described, and so that's a separate state of matter in which vacancy dislocations are not subdimensional. You have fractons, but dislocations can move two-dimensionally. On the other hand, normal crystal, the one I described, has U1 symmetry not broken, and so then you have dislocations that are one-dimensional because there are no vacancy interstitials, those are gapped. And there's a phase transition between these, and one can describe that phase transition. Let me skip over these details. The only message here is that two types of, immediately this connection tells you, just like there are two types of crystals, supersolid and non-supersolid, there are two types of Fracton phases. And so we call it symmetry-enriched Fracton phases, meaning it's Fracton phase which has been enriched by the number conservation of atom symmetry. You can, now that you understand phases of matter, you can start talking about phase transitions out of this fractonic phase of matter. So for example, you can think about thermal phase of matter. So you now, it's really a classical theory. You're now at finite temperature, so it's really dominated just by thermal fluctuations. You can start out in the Fracton phase of matter that I described, and what you can do is you can both condense dislocations. If you condense dislocations or dipoles of fractons, you get a new phase of matter, which is no longer fractonic, and there's a phase transition to that new phase. And then you can, in that phase, you can now condense disclinations or condense what were fractons. And there's a detailed theory that we developed, which is kind of a vector sign-Gord model that describes this transition. I don't have time to discuss it in detail, but it has a nice renormalization group flow diagram that allows you to describe this two-step phase transition. And this directly reproduces what the famous theory of Kostelis, Thales, Halpern, Nelson, and Young of two-stage melting of a two-dimensional crystal. Kostelis-like theory of two-dimensional melting. Except, okay, so there's really no difference. It's just a reformulation in terms of these dual degrees of freedom. You can have a quantum version of this where you, again, condense dislocations. Here's a quantum dislocation field. It's a vector field. We have a quantum theory of its description. It's some kind of a funny superconductor model coupled to a tensor gauge theory. You can condense these defects, and you can get some kind of a generalized phase diagram in which there's a fractonic phase which is U1 symmetric. That's the commensurate crystal. Fractonic phase that's super solid. There's a superhexatic when you both condense these dislocations. It has to become a super in the sense of condensate. And then if you condense disclinations or you condense fractons, you'll get a superfluid. So with that, let me just summarize and conclude. So what I told you about is a new class of fracton quantum liquids. They're kind of the most striking features. They have local excitations, quasi-particles that are immobile or are subdimensional. They move in some subspace, 0, 1, or 2-dimensional subspace, or the full dimensional space. My main message is in the form of this, I've described the duality between the seemingly very exotic state of matter to something that's very familiar, namely a quantum crystal of topological defects and phonons, and it's summarized in this diagram dictionary here. And there are various phase transitions that I've mentioned briefly, leaving this Fracton state of matter, and then there's a variety of questions that we're still exploring. And so with this, I'll stop and thank you for your attention. Right, so to the extent that there's a just directly, I predict that phase just by knowing that in principle there's a supersolid phase. I don't have any more to add than what we know about supersolid. It's been a holy grail with lots of false smoking guns, but as far as I know, there's no, while it appears, I think in simulations, there's no experimental realization of what parameter do you tune in the real system to really realize a supersolid phase of a crystal. But my point is, if you were to realize it, you would realize, and you would have a phase transition between the two, you would have a phase transition between two fractonic phases with the distinguishing property is mobile and immobile dipoles.
Questions? Actually, I have one. So if I understood correctly, you were often trying to use insights from elasticity theory and bring those insights over to the Fracton problem, but can one go in reverse and use insights from Fractons and try to say something new about?
Yeah, I guess I would say two things about that. So one, I work in elasticity, generalized elasticity, and have done so for many years. And as far as I know, there is no statement in the literature about immobility of disclinations. So that's something I learned thinking about fractons, conjecturing that there's this connection. and trying to understand really in the crystal language why disclinations cannot move as a disclination. So that's one. The second thing is, you can say this is an extremely compact formulation of highly non-trivial coupling between disclinations and dislocations and phonon degrees of freedom. For example, I don't know if I'll get to it, but there's this equation that, let's see. There's this equation which is actually an Ampere's law equation that you derive from the gauge theory. It's kind of a beautiful, in fact, I derived it with Christina Marchetti in 1998, thinking about melting of vortex lattices in superconductor. And this equation is kind of an interesting equation. It says, it's the left-hand side, if the right-hand side was 0, it would be a continuity equation for vacancy interstitials. But actually, the right-hand side is not 0. So what is the right-hand side? It's the trace of this dipole current. And so what that right-hand side says is, it's very non-trivial coupling between the motion of dislocations and vacancy interstitials. It basically summarizes as quite a non-trivial process. It says, if I have a dislocation climb, I will generate vacancy interstitials. It'll be a source for vacancy interstitials. So there are things like that that are extremely natural in this gauge theory formulation.
So a lot of your results, you focus on 2D systems. If
Yeah.
you consider 3 dimensions, does that make things a lot more complicated? Does that change the mobility?
Yeah, so if you take a crystal, 3-dimensional crystal, now topological defects are lines, not points. And so if you just go and carry that through, and Michael Pretko and Shreya Pai have done that, just sort of following my work with Michael, it's a straightforward extension, but it's non-trivial extension. So what you get is not, you'll now have some fractonic theory of lines rather than points. So it's a theory, you've generated it. So it doesn't give you the fractonic model, 3-dimensional fractonic model with point defect. However, like this, on the other hand, this formulation of vector gauge theory, this coupled vector gauge theory is directly generalized to any dimension. So you see I have here 2 flavors of capital E and 1 flavor of E. If I wanted to be in D dimensions, I would have D flavors of capital E coupled to D components of 1 additional vector gauge theory. So you just generalize this lattice. So having derived it only in 2D, 2 plus 1 dimension, you can then immediately look at that model and use the lessons you learn from it to write down a more high dimensional model.
Okay, if not, let's thank you again.
Thank you.